Alright, when we're trying to graph exponential functions, there are a couple key points we need to know, but first let's just take a look at the shape. A classic exponential graph is this one. There's your graph right there, y equals 2 to the x. So 0, 1, and 1, 2, 2, 4, 3, 8, these are all key points. And the area where sometimes we forget our math is back here. If you have 2 raised to a power of -1, that's 1/2. So if you were filling out, say, a t-chart and x was -1, your 1/2 would be your y value. That's that point right there. So that's one thing, is just knowing the basic shapes. Also, sometimes graphs go down. This is the graph right here. You could write it differently. You could say the base is 1/4. Your base is a fraction between 0 and 1. Up here, your base was a whole number bigger than 1. And so if you have two shapes, they obviously have to have two kinds of vocabulary. If it goes up as it goes to the right, we call that an example of growth. Growth goes up. Decay just means that it goes down as it goes to the right. The other thing about all of these graphs, notice a basic graph doesn't go below this line. There's no exponent that can make a positive number negative. And so you have these lines that are called asymptotes that are very important on each of the graphs. And for the most part, they stay here on the x-axis. Remember, a horizontal line, please, is y equals. But then as you start shifting and moving your graph, the asymptotes will move, and that's going to affect your range. So let's try a couple examples. Say I wanted to do y equals 3 to the x. These are your key points. -1, 1 over base. 0, 1, and 1 base. What are we talking about when we talk about the base? We're talking about that number right there. If I plot -1, 1/3, somewhere there. If I plot 0, 1, it's right here. And if I plot 1, 3, it's here. The general shape goes up because this is an example of growth. It will, however, never go below this line. That's your asymptote. So I'll do another one. What if I took a look at the graph of y equals, let's do 1/2 as our base, 1/2 to the x. So you have to think carefully here. 0, 1, that's clean. That's a given. 1 base means that 1 and 1/2 is going to be, okay, right here. It's this direction it sometimes throws people. -1 raised, oops, sorry about that. 1/2 raised to a power of -1, remember, flips the fraction. It's the same thing as 2 over 1 or 2. So -1, 2 is the point on this end. So as I go backwards in this direction, it drops. It, remember the word, decays as it goes to the right, and it will never go below that line. So that's an example of growth and decay, and that's what this looks like in practice. Just remember, a fraction raised to a -1 exponent flips the fraction, and that's why the left side gets bigger when you have a fraction base. Now, a couple things are going to come up. You're going to be given a normal graph. This right here, you'll sometimes see abbreviated as PF. That's the parent function. That's your main graph. There is no transformation there. But if you do something up in the exponent, that moves you left and right. And if you remember from previous units, you do the opposite. X plus 3 moves you left 3. If you had something at the end, that number is going to move you up or down. If you're adding, it'll move you up. If you have decay, the same kind of thing is going to happen. This we'll call the parent function, PF. If I see that I have something in the exponent, in this case, a -3 would move me right 3. You do the opposite when it's in the exponent. If I see a number outside and it's minus, this is going to move me down 3. So that's part of the transformations. Now, it can get a little crazy when you do move up and down. You know, I want to remind you of this from the notes. My main function is the pink line. So I had 0, 1, 1, 3. That's my main graph. When it moved up 2, notice that the asymptote had to move up 2. And when I had a down 4, what is it that's moving? It's these key points. So the parent function again is pink. If I move down 4, I count 1, 2, 3, 4. I have this other point, 1, 3. It's going to move 1, 2, 3, 4 down. And that's how I get my movement. A suggestion is to remember, if the asymptote is normally 1 away from this key point, when you count down 4 to that point, go down 1 and you have your asymptote. Why is that important? Because the range of this orange graph is going to be everything from 1, 2, 3, 4. So this is -4, -4 up forever. In a soft bracket, because you're never going to equal the asymptote. If I looked at the green graph and I was looking at the range of it, When I moved myself up to the asymptote, the original from the pink, moved up 2 as well. So here I am at 2. The range is going to be from 2 and up forever. That's supposed to be an infinity, but a soft bracket on an asymptote. So anytime you have a number out here moving yourself up and down, it's going to move the asymptote, which then will affect your range. So what do you do when you have them all together? There's kind of a good order to go in, and this is a suggestion. This is the top and the back of your worksheet if you wonder where it's coming from. If there's something in the exponent, talk about that first. So the first thing I'm going to do is I'm going to move left 1. If there's something out in front, talk about that next. That's going to reflect over the x-axis. Yes, it's flipping. I'm going to try to say it properly. And then at the very end, that part's going to make you go down 5. Try the same order here. Notice there's nothing in front. That's my main graph right there. So the first thing I'm going to do is I'm going to go left 2, remember opposite in the exponent, and then I'll go up 4, or sorry, up, oop, I think that's a 1 right there, sorry, up 1 in the graph. Over here in this problem, I'm going to start off by going right 1, because that's in the exponent. Out in front, I'm going to double everything. This is the idea of a vertical stretch. Going to vertical stretch by 2, doubling. And then the last thing at the end is I'm going to go down 2 units because I have a -2 in it. So just some things to think about. Also, some people really just like a nice plot to point, or point to plot, sorry. And if you look at an x that would make the exponent equal to 0, it helps. So if I was in this problem and I looked at what would make the exponent 0, I would try an x value of -1. And if I plug that in here, oh sorry, this is supposed to say down 3 here. Sorry, I said 5. If I try to do the math on this, be patient. You have -2 raised to the 0 minus 3. Well, that's, look at this one, -1 minus 3, so that's -4. In this problem, the x value that would make the exponent equal 0 is -2. So you're going to have 1/3 raised to the power of 0 plus 1. 1 plus 1 is 2. If I look at the last problem here, if I look at an x value that would make the exponent 0, it's 1. So if I multiply that out, I have 2 times 3 to the 0, so that's like saying 2 times 1 or 2, minus 2 is 0. These are just specific points that would be on the graph if you want to get real mathy. I think the main thing, though, is to recognize your shape. If it goes down as it goes to the right, it's called decay, and that's because your base is less than 1. If it goes up as it goes to the right, it's called growth, and that means your base is a number bigger than 1. Happy graphing.